All right, we're recording now. I would like to continue. I'm going to finish the Z inverse today. But I'm going to show you something. All right. Let's say, I don't know how many people I have here. Let's say this is example 3.25. So we have AZ equal to Z squared over Z squared plus 1. Okay. Well, I mean, we already know. We know from the table that AN is the inverse of AZ, and that is cosine n pi over 2. Okay, just look at the table. Now, we want to use the residue theorem to do it. So let's use the residue theorem. I mean, sometimes the residue theorem is helpful. I mean, it's a little bit easier. Sometimes it's not. So if I do the residue theorem, so AZ has two simple poles plus or minus I. Okay? Because this one is Z squared over Z minus I, Z plus I. And they are simple. So what is, so if Z0 is I, what is alpha 1? Remember, what is alpha 1 is the limb as Z approaches I of Z minus I, Zn plus 1 over Z minus I, Z plus I, and this over that. So that is lim as Z approaches I, Zn plus 1 over Z plus I. That is I to power n plus 1 over 2I. Okay? And now if I take 0 equal minus I, alpha 2 is lim as Z approaches minus I, Z plus I, Zn plus 1 over Z minus I, Z plus I. Cancel, cancel, and that is going to be minus I to power n plus 1 over minus 2I. Okay? All right. Well, what do we know? We know that I is e to the I of pi over 2. Why? Because this is equal cosine of pi over 2 plus I sine of pi over 2, and that is I. You see? Similarly, minus I is e to the minus I pi over 2. Okay? You see what we're doing? So now, so AN is alpha 1 plus alpha 2, and alpha 1 was I to power n plus 1 over 2I, okay? A plus minus I to power n plus 1 over minus 2I. So this is 1 over 2I, I to power n plus 1 minus minus I to power n plus 1. Okay? And that is 1 over 2I of I is this one. So this is going to be e to the I pi over 2 to power n plus 1 minus e to the minus I pi over 2 to power n plus 1. You see what happened? Well, this is 1 over 2I e to the I n plus 1 pi over 2 minus e to the minus I n plus 1 to pi over 2. Okay? So what is that equal to? That is 1 over 2I cosine n plus 1 pi over 2 minus a plus I sine n plus 1 pi over 2 minus, now we're talking about this, cosine n plus 1 pi over 2 plus I sine n plus 1 pi over 2. You see this and this cancels out, and we have 2I sine n plus 1 pi over 2 over 2I, and that is sine n plus 1 pi over 2, and that is cosine n pi over 2, as we got from there. Okay? Any questions? So we did it in two different ways. We did it using the table directly. And if we use the residue theorem, you can, but it's going to take some work, some verification. All right? So that is a very sophisticated way of doing it. But here where we are. Any questions so far? Any questions? Yes. All right.
Hey,
Okay.
Professor,
Yes.
when you write sine of n plus 1 times pi over 2, you really mean all of that in parentheses, right? Yeah, that's I mean, I figured. I just make sure.
Okay. Yes, it is. And I did not want to really put a bracket like this and confuse it with this bracket. You know what I mean? The Z transform.
Yeah, I figured. I just wanted to check.
That's okay. That's all right. Any other questions? I should have put a bigger parentheses, but that's okay. All right, you got it. So Euler formula, it's really, really important, right? This one, it's very important. I think they talk about Einstein relativity theory. I think Euler formula for the exponential is more important and comes into more use. All right. So convolution method. Okay. So we have, remember, Z of U star V is UZ times VZ. Correct? Recall that. Hence, hence, U star V of N, this is the original sequence, is Z inverse of UZ times VZ. Okay? Let's consider example 3.28. Consider AZ equal to Z squared over Z minus 1 times Z minus 2. Okay? And this is for Z bigger than 2. All right? Because the radius of this one is Z bigger than 1, Z bigger than 2. So Z has to be bigger than the max of the 2, which is 2. All right? So we're going to write this as UZ VZ, which is Z over Z minus 1 minus Z over Z minus 2. You see what I did? Okay. So what is, so UN is Z inverse of Z over Z minus 1, correct? And that is 1. And Vn is Z inverse over Z minus 2, and that is 2 to power n. All right? Okay? So therefore, Z inverse over Z squared over Z minus 1, Z minus 2 is UN star Vn. That is 1 star 2 to power n. Correct? And that is m equals 0 to n, 2 to power n minus n. Okay? So that is a convolution of 1 convoluted with 2 to power n. And that is, I'm doing the summation respect to m. So 2 to the n, m equals 0 to n, 1/2 to power n. Now there is a typo I noticed for this kind of equation. When they said the Galli proof of the book, they messed up the notation. And I'm gonna have to do an errata, I guess, because of that. So trust me, I knew what I was doing, but they, they said that they're Galli proof, and they ask you to go through it. And after reading the book a zillion times, you get tired, and then there is a mistake. So this is 2 to the n. So let me do the calculation here. So it is equal to, I'm going from here to here, 2 to the n. It's gonna be 1/2 to power n over 1/2 minus 1 from m equals 0 to m equal n plus 1. Okay? And 1/2 minus 1 is minus 1/2. So it will be minus 2. So that is minus 2 times n plus 1 of 1/2 n plus 1 minus 1. Okay? And that is minus 2n plus 1 times 2 minus n minus 1 minus 1. All right. Multiply these together. This is minus 2n plus 1 minus n minus 1 minus 2n plus 1. And that is 2n plus 1 minus 1. There you go. Okay. So the book really messed up these stupid, they messed up my notation. Oh, I cannot believe that. All right. Any questions? So I am done with the Z transform. This is very important for it. There's a big section on engineering application for those who are in engineering now. You should be able to read it and understand everything in it. Okay, it's really easy read. All right. Now we're gonna move on to chapter 4. I promise to have your exam graded and ready by tomorrow. Okay? Or by the end of today. That's what I meant. We'll be ready tomorrow morning when you wake up. I didn't get to ask you about how did the exam. What did you think of the exam? Chapter 4. Systems. Okay. So we're gonna consider the system. It could be nonlinear. X1 of n plus 1 equal f1 of n, x1 of n, all the way to xk of n, x2 of n plus 1 equal f2 of n, x2 of n, xk of n, all the way to xk of n plus 1 equal to f of k of n, x1 of n, x1 of n, all the way to xk of n. Okay? Using vector notation, with x of n equal x1 to xk, we have x of n plus 1 equal to fn x, where fn x equal f1 to fk. Okay? So we can write the system like that. Now, higher order difference equations can be written into system by using the transformation if we're gonna use the transformation, it's gonna be xi of n equal to x of n plus I minus 1, where I equal 1 to all the way to k. So we make a change of variables. Okay? So let me write it again here. Okay? So again, we have xi of n equal x of n plus I minus 1, I equal 1, 2, all the way to k. All right? So for example, let's have xn plus 4 plus b3, xn plus 3 plus b2, xn plus 2 plus b1 of xn plus 1 plus b0 of xn. Equals 0. Okay? So here, k is 4. So we're gonna take xin equal xn plus I minus 1 for I equal 1, 2, 3, and 4. You see what we did? All right, so for I equal 1, I get x1 of n equal xn. I equal 2, x2 of n equal xn plus 1. I equal 3, x3 of n equal xn plus 2. And I equal 4, x4 of n equal xn plus 3. Okay? So let's draw a line. Then what? Then this is the transformation. Then x1 of n plus 1 equal to xn plus 1, but xn plus 1 equal x2 of n. You see that? Okay? x2, now move on to x2 of n plus 1 equal to x of n plus 2, but xn plus 2 is x3 of n. Okay? And x3 of n plus 1, x3 of n plus 1 equal xn plus 3, as xn plus 3 equal x4 of n. Okay? And then now, finally, here, x4 of n plus 1 equal to xn plus 4. And now let's take a look at here. Xn plus 4. What is that? That is minus b3 xn plus 3 minus b2 xn plus 2 minus b1 xn plus 1 minus b0 x of n. Well, we should eliminate all those. So this is minus b3. What is xn plus 3? xn plus 3 equal x4 of n minus b2 xn plus 2 xn plus 2 equal to x3 of n minus b1 xn plus 1 is x2 of n minus b0 x of n x1 of n. Okay? So the new system, the system is, let's read it from here, x1 of n plus 1 equal x2 of n, x2 of n plus 1 equal to x3 of n, x3 of n plus 1 equal to x4 of n, and x4 of n plus 1 is from here, will be minus b0 x1 of n minus b1 x2 of n minus b2 x3 of n minus b3 x4 of n. That is your system. So that system represents this equation. Okay? Any questions? So in matrix form, So we let x of n equal to x1, x2, x3, x4, and A, this is a matrix, equal to x1 of n plus 1 will be 0, 1, 0, 0. X2 of n plus 1 will be 0, 1, 0, 0, 1, 0, 0, 0, 0, 1, and then minus B0, minus B1, minus B2, minus B3. Okay, and therefore this system can be written as x n plus 1 equal a xn. Okay. All right. Any questions? Let's take a look at xn plus 2 minus 3xn plus 1 plus xn equals 0. Let's take a look at the system. Now, how would you solve the system? If you look from xn equal lambda to power n, then this will be lambda squared minus 3 lambda plus 1 equals 0, and you get lambda equal 1, lambda equal 2, correct? Do you see what happened here? And now let's transform into system. So we have I equal 1 and 2. So we know x1 of n is xn, x2 of n equal to x of n plus 1. All right. x2 of n okay. So now x1 of n plus 1 equal xn plus 1 equal x2 of n, and x2 of n plus 1 equal x of n plus 2. That from here, that will be 3xn plus 1 minus xn, and that is xn is minus x1 of n plus 3xn plus 1 plus 3x2 of n. So the system, the matrix A is 0, 1, minus 1, 3. Okay? So in terms of system, because you can write this one as x1 n plus 1, x2 of n plus 1 as 0, 1, minus 1, 3, x1 of n, x2 of n. Okay? Let's try to look for the eigenvalues. I know we have not defined the eigenvalues, but you all know what an eigenvalue is. Let's take a look at a minus lambda r. That will be minus 1 1, minus 1, 2. And the determinant, oh, sorry, I'm using lambda, will be minus lambda 1 minus 1, 3 minus lambda. So thus determinant of A minus lambda I is minus lambda 3 minus lambda plus 1 equals 0. And that is lambda squared plus 3 lambda minus 3 lambda plus 1 equals 0. Do you see it? Do you see the two, the relationship between the two? Okay. So the solution will depend on the eigenvalue of the matrix A, like here, correct? Okay. So this is what we're going to be studying. Looking at matrices, I mean systems, and see how their solution evolve. Any questions? All right. So we did this transformation. All right. So now let's take a look at system more in general, trying to study their solution. So now we're going to consider the non-homogeneous system xn plus 1 equal axn plus gn. So these are functions. And the A could depend on n for now. And that is 4.2.1. And here, xn is x1 of n, xk of n, and gn equal to g1n, gk of n. So this is a system, and A is a k by k matrix. Is a k by k matrix. Okay? So let us consider the homogeneous system xn plus 1 equal axn. Here, A is k by k constant matrix. That is, none of its entry depends on the variable n. Okay? And we're going to assume x of n naught equal x naught. Okay? All right. Then the solution Okay, I am calling this system 4.22. 4.2. That is this system here, the name of it. So the solution of 4.2 is xn equal to a to power n minus n naught okay, x naught. All right, and n belong to n naught. Remember what n naught is. Let me remind you of what n naught is. Is n naught plus 1, etc. If n naught is 0, that means your set is 0, 1, 2, 3, 4, 5, and so forth. Okay? Now, we are assuming, for example, x of n naught is a to the n naught minus n naught x naught. That is a to power 0 x naught, and we're assuming a to power 0 is the identity matrix, and that fair. So we're gonna study this matrix. What does this matrix look like? How do we compute it? You see, a to power n minus n naught is not that you take the matrix A, you raise it to power n minus n naught. Okay, it's not the same. All right, I mean, in some sense, you will see it's not really. All right, and you can easily verify that xn plus 1 is, look, we are looking here, is a n plus 1 minus n naught x naught. That is a times a n minus n naught x naught. That is a xn. So because this one is xn. Okay? So it's indeed a solution. But how is the matrix A defined? How do we compute the matrix A? Well, if the matrix A is diagonalized, then it is easy. For example, let's say I'm gonna flip the board. I'll give you a minute or so to catch up. All right. So let's say we have xn plus 1 equal to 2, 0, 0 minus 3, x1 of n, x2 of n, and with x naught equal x01, x02. Okay. So here xn is x1 of n, x2 of n. So this is a vector. So A is 2, 0, 0 minus 3. It's diagonal. So note that this is a diagonal matrix. Okay. So a squared is a times a. You're gonna get 2 squared 0, 0 minus 3 squared. You go ahead and multiply it. A cubed is a times a squared. That is 2 cubed 0, 0 minus 3 cubed, and so forth. So you're gonna get a to the n is a times a n minus 1, and that is 2 to power n 0, 0 minus 3 to power n. Okay? So that is an. So an minus naught is gonna be 2n minus n naught, 0, 0, minus 3n minus n naught. And so the solution is xn equal an minus n naught, x naught, that is 2n minus n naught, 0, 0, minus 3 n minus n naught times x naught, x01, x02. Okay? So that is the solution. But you can only do that. We were able to do this simple calculation because the matrix was diagonal. That means all main diagonal entry are 0. Okay? All right, let's take 5 minutes break and we'll come back. All right, let's see if anybody chatting. All right. Okay, let's take 5 minutes break. I'm getting tired. Recording is taking. Well, I should be sure to send us. It's not up to us. I don't know. What? I see your eyes. I have never seen a plant that its flower lasts that. It's been over like this for 1.5 months. This. All right, I'm back. Okay. Oh, by the way, from this one here, I mean, so we have xn equal to 2n minus n naught, or was it, yeah, 0, 0, minus 3n minus n naught, x01, x02. So that means x1 of n is x02, no, x01 times 2 to power n minus n naught, and x2 of n equal to x02 minus 3n minus n naught. Correct? And then the solution, xn is c1 x1 of n plus, is x1 of n plus x2 of n, and that is x01 2n minus n naught plus x02 minus 3n minus n naught. Now compare this to xn plus 2 minus 3xn plus 1 plus xn equals 0. So if we have xn0 equal x0, correct? I mean, here you will have two initial conditions, correct? You're going to have two initial conditions. So the solution, remember lambda squared minus 3 lambda plus 1 equals 0. Lambda equal, oh no, this is different problem. I'm sorry. No, this is totally different problem. Yeah, it's different problem. So let's go back to what we did before. X squared, lambda squared minus 3 lambda plus 1, and lambda equal to 2. So it will be C1, 1 to the n plus C2, 2 to the n. You see, this is related to this stuff here. You see that? So they are similar if you are given the initial conditions. So don't be scared. Okay. So I'm gonna get rid of this. Definition. Let A be and K by K constant matrix. Okay. We say lambda is an eigenvalue of A if there is a non-zero vector V such that AV equal lambda V. Okay. Now, the vector V is called the corresponding eigenvector. Now, we say that lambda V are eigenpairs of A instead of mentioning all these details. Okay. All right. So again, let's take a look at xn plus 1 equal AXN. And I'm in a new section, so we're gonna call this 4.25. Okay. 4.2.5. Okay. Now, where A is a K by K constant matrix. Now we will see that the solution of 4.25 will, we will see the solution constructed from the eigenpairs of A. Okay? Now assume a solution of 4.25 of the form x of n equal v lambda to the nth, and v belong to Rk. Okay? And lambda is in R. That means v is a vector. So what I'm saying is that v is v1, vk. Then xn plus 1 equal v lambda n plus 1 equal to lambda v lambda n. Okay? Lambda is a scalar. Okay? Here is 4.25. All right. Substitute into 4.2.5. And then we get lambda v lambda n equal a v lambda n. Correct? That is a v lambda n minus lambda v lambda n equals 0. So this is a minus lambda I v lambda n equals 0. Since lambda n is never 0, we have a minus lambda I v equals 0. Okay? And this is if and only if determinant of a minus lambda I is equal 0, because v is a non-zero vector. Okay? So there we go. So that brings us back to the eigenvalue, eigenvectors. All right? Okay? Thus, we have shown that if v naught, lambda naught are eigen pairs of A, then xn plus 1 equal v naught lambda naught to the n. Okay? Which is lambda 0 to the n v0 is a solution of 4.25. Okay? So it's a solution of that. We get our notes. All right. So this is what we have. So now let's talk about constructing the solution. This is theorem 4.2. Okay. If lambda 1, lambda k are distinct eigenvalues of A of the k by k constant matrix A, then the corresponding eigenvectors v1, v2, vk are linearly independent. Okay, or linearly independent. So you can see I have a nice proof for that in the book. Okay. Another theorem 4.23, this is distinct eigenvalue. Okay. Suppose lambda 1 to lambda k are distinct eigenvalues of the k by k constant matrix A with corresponding eigenvectors v1 to vk, then the general solution of 4.2.5 is x of n equals c1 v1 lambda 1 to power n plus c2 v2 lambda 2 to power n plus ck dk lambda k to power n, where ci I equal 1 to k are constant. They are given by the initial condition. Okay. All right. So we're getting into the interesting stuff now. Okay. Now, so I'm gonna do some remark. Okay. First of all, if we let phi I equal to vi lambda I to n, I equal 1, 2 to k, then we may construct the matrix phi, okay, phi n by taking its columns to be okay, to be phi I, and hence the matrix phi is phi 1, phi 2, phi k. Okay. To each column phi I solves 4.2.5. That is phi I of n plus 1 equal to a phi I of n. Each column. Okay. Let me take a look at an example and see how far I can go. Let's let xn plus 1 equal to minus 4, 1, 1, 1, 5, minus 1, 0, 1, minus 3 times x1, x2, x3 of n. Okay. So if I am gonna look at a minus lambda I, the determinant, that is minus 4 minus lambda, 1, 1, 1, 5 minus lambda, minus 1, 0, 1, minus 3 minus lambda. Okay. And that is minus 4 minus lambda times 5 minus lambda times minus 3 minus lambda Okay. Plus 1 minus 1, and I'm gonna go this way. I'm gonna erase this, and this will be, I'm gonna erase this and this. So what I'm gonna have, minus 3 minus lambda minus 1 equals 0. I did it along this, the first column. Okay. So this is minus 4 minus lambda of minus 15 plus lambda squared, and have minus 5 lambda plus 3 lambda plus 2 lambda plus 1 and plus 4 plus lambda equals 0. And this is going to, this is gonna be lambda plus 3, lambda plus 4, and lambda minus 5 equals 0. Okay. Well, if you take minus 4 and put it in here, you automatically lambda equal minus 4, you will get 0. And then you can factor it out. You can work something out. Okay. So I'm gonna do some work here. Let me show you how to find the first eigenvector. And then I'll wave my hand through the other two. Okay. All right. So let's take lambda equal minus 3, then a minus lambda I v equal to minus 4 minus lambda 1 1 and one 5 minus lambda minus 1 and 0 1 minus 3 minus lambda times v1 v2 v3 equals 0. Let me call this v, I don't want to call it ABC equal to 0. So here v is ABC. Okay. So I'm gonna have minus 4 minus lambda times A plus B plus C equals 0. A plus 5 minus lambda B minus C equals 0. 0A plus B plus minus 3 minus lambda C equals 0. Okay. So if I take lambda equal minus 3, then this becomes minus A plus B plus C equals 0. And the second equation becomes A plus 8B minus C equals 0. And this one becomes B equals 0. Because I'm putting lambda equal -3, that will be -3 plus 3 times C equals 0. So I have B equals 0. If B equals 0, then I have minus A plus C equals 0, and A minus C is equal 0. Okay? B equals 0. Let's see. Minus A plus B plus C equals 0. So I got B equals 0. Okay. So let's see. Do I have any issue here? Okay, so I'm having the issue is lambda equal -3. I'm having this issue. B equal to 0. Oh, so either equation give me A equals C, either equation. So what do you want to take C to be? If I take C equal 1, then A is 1. So the vector V is 1, 0, 1. There we go. So phi 1 is, what did we say phi 1 was? The eigenvector, okay, it's gonna be V lambda 1 to the n, that is 1, 0, 1 times -3 to power n. That is your phi 1. Okay? And so for lambda 2 equal to, so let me call this is V1. For lambda 2 equal V2 lambda 2 to power n. So we're gonna have, I'm gonna skip it. 10 minus 1, 10 minus 1, 1 times -4 to power n, because what do we have? We have lambda equal -3, lambda equal -4, okay? And so that is not, that is phi 2. And phi 3 is V3 lambda 3 to the n, and that is 1, 8, 1 times 5 to power n. So the solution is xn equals C1 V1 lambda 1 to the n plus C2 V2 lambda 2 to the n plus C3 V3 lambda 3 to power n, and that is C1 101 minus 3 to power n plus C2 10 minus 1 1 times -4 to power n plus C3 1 8 1 times 5 to power n. That is your solution. And remember what xn is. Xn is x1, x2, x3. Okay? And now the vector phi is phi1, phi2, phi n, phi3. And so the vector phi, I'm going to write it here, is -3 to the n, 0, -3 to the n. Phi2 will be 10 times -4 to the n minus -4 to the n, and then -4 to power n, and that will be 5 to power n, 8 times 5 to power n, and 5 to power n. So this is your matrix field. Okay? And I'm gonna verify one thing for you. I'll let you catch up with this. Okay? So you see these are the column. All right? And remember, you don't need to add this equation. That means any of these two equations will give you A equals C, which is consistent with both equations. A equals C will make each equation a true statement. Now, let's verify that each column. So let's verify that phi1 of n plus 1 equal A phi1 of n. And here, phi1 of n is, we got it from here. That is phi1 of n, -3 to the n, 0, -3 to the n. So what is phi1 n plus 1? That is -3 n plus 1, 0, -3 n plus 1. What is A phi1 of n? That is -4, 1, 1, 1, 5, -1, 0, 1, -3 times -3 to power n, 0, -3 to power n. So hopefully I will get this one. So what is that? That is -4 times -3 to the n plus -3 to the n. That's for the first column. Then I have -3 to the n, 0, minus -3 to the n. And then I have 0, 0, -3 times -3 to the n. Well, what is that? That is -4 plus -3 to the n. That is, if I factor -3 to the n out, I'll get 1 minus 4, and I get 0, and I get -3 to the n plus 1. And that is, this one is -3 to the n times -3, and that is -3 to the n plus 1. So you will see it satisfies this. So this is minus 3 to power n plus 1, 0 minus 3 to power n plus 1. So actually, indeed, it is solution. Okay. So the eigenvalues, eigenvector play a very important role in solving systems, specifically linear system with constant coefficient. We shall see later that if the matrix A depends on n, that may not be the solution, or at least for like stability result may not hold if the matrix A depend on n and so forth. I think I'm gonna stop here. Are there any questions? Then I'll pick it up from here. Any questions? I'm stopping the AI. I'm stopping recording.